Hi everyone, welcome to my YouTube channel Sri Sai Tech Edu, Read Lead Success. And I am so excited to share this journey with you. This is my very first video and I am here to share something truly valuable for all students and tech enthusiasts out there. In this channel, I will be covering the subjects as per the syllabus of VTU. You will find detailed explanation, tips and resources to make learning easier and more engaging. I'll also share practical tips, tutorials and insights from my own academic and project experiences. My goal is to make this topic simple, fun and accessible for anyone passionate about learning and growing in these fields. So if you are curious about electronics, computers or just love learning about technology, make sure you watch all my videos from now and don't miss any updates. And if you have any specific topics you would like me to cover, let me know in the comments below. To start with, I am starting with the subject Network Analysis and Control Systems, which is the 4th semester subject of Electronics and Computer Engineering. The module 1 consists of 2 chapters, Basic Circuit Elements and Network Theorems. In Basic Circuit Elements, there are different topics to be learnt, that is Introduction, Circuit components. Some different circuit components like resistor, capacitor and inductor will be studying, and definitions of some important definitions, sources of electrical energy and some transformations like source transformation, general network transformation, mesh and node analysis to transform or change the circuit to a easy form to find some values or to a new form from the original circuit. Introduction. The phenomenon of transferring charge from one point in a circuit to another is termed as electric current. If there is a transferring of charge from one point to other, then it is known as electric current. When the charge is moving from one point to other, there are electrons also moving with some rate of flow of free electrons. Like electric current in an element is the time rate of flow of free electrons in the element. Like electric current is produced when transferring of charge from one point to other, then there will be a number of electrons also moving with this charge, so that electric current is produced. Electron has a charge 1.6021 into 10 power minus 19 coulomb. It follows that a current I of 1 ampere corresponds to the motion of I is equals to Q by T, rate of change of charge, where Q is equals to number of electrons into one electrons charge E. Therefore, N is equals to know number of electrons in any cross section in 1 second, then N is equals to 1 by E is nothing but 1 electron charge, that is 1.6021 into 10 power minus 19 coulomb, that is equals to 6.24 into 10 power 18 electrons per second in any cross section of a path. Now let us see a video. Before that, let us see the circuit. What is there? Battery and a bulb and a switch. When a switch is on, what happens? The current flows. When the current is flowing, what I told, that there will be a charge and electrons also will be moving. Means the current is moving in this way and the electrons will move in the opposite direction of the current, so that the electric current will pass and the bulb gets on. This is the way how the electrons and current direction we can see in this video. The materials may be classified as conductors, insulators and semiconductors. Conductors, where availability of free electrons is very large, as in the case of metals. Where there are many electrons present, then there will be the more electricity produced. Nothing but conductivity is more. Free electrons are more, the conductivity is more. And the conductors is nothing but there are many free electrons present, like copper, gold, water, graphite, all other metals. These all are conductors. Then insulators. where the availability of free electrons is rare, as in case of glass, mica, plastics, etc. In these insulators, electrons are rare and maybe no free electrons are present, like glass, plastic, ceramic, rubber, paper, fabric, and many more. Other materials such as germanium and silicon, called semiconductors, plays a very significant role in electronics. Semiconductors is nothing but it is between conductors and insulators, and free electrons are present, and conduction is also possible. And there is a silicon, this is the germanium. We'll now see two important definitions of this: conductivity and resistivity. Conductivity is nothing but ability of the path or element to transfer electrons. If the path is transferring electrons, means the material or something is conductivity is more, and it is known as conductivity. Resistivity is nothing but we are resisting the circuit to the passage of the electrons. So the only required number of electrons will be passed, and other electrons are not allowed. So that is known as resistivity. Resistivity is the inverse of conductance. Nothing but if resistivity R is equals to, it is the inverse of conductivity. Conductivity is given by the notation sigma, like this. In circuit analysis, we are concerned with the four basic things of electricity. In the circuit analysis, there are main four things of electricity we are concerned with. That is electric charge, that is Q of t, magnetic flux phi of t, electric potential V of t, and electric current I of t. The current through a circuit element is the time derivative of electric charge. Nothing but I of t is equal to d by dt of Q of t. As you have seen before slides also, I is equal to rate of change of Q. Nothing but unit of charge is what? Coulomb. And unit of current is Coulomb per second. Why? Because Q is Coulomb and T is time. Time has a unit of seconds. So Coulomb per second, or it is termed as ampere and simply abbreviated as A. The potential difference between the terminals of a circuit element in a magnetic field is equal to the time derivative of the flux phi of t. That is V of t is equals to d by dt of phi of t. The unit of potential is Weber per second. Why? Because phi of t is Weber and t is second, Weber per second, or simply we call it as volts. Voltage is the energy required to move 1 coulomb of charge through an element, that is V of t is equals to dW by dQ. The instantaneous power P of t delivered to a circuit element is the product of the instantaneous value of voltage V of t and current I of t of the element, where P of t is nothing but is equals to V of t into I of t, nothing but voltage and current. The unit of power is watt. The energy delivered to a circuit element over the time interval T0, T is given by E is nothing but energy in the terminal. The interval is T0 to T. Integration to intervals T0 to T, P of x dx. Why? Because power, if we integrate power, then we get the energy. So P of x is nothing but what? V of t into I of t. We can write V of x into I of x dx. The unit of energy is watt second, or also we can the unit can be is also given as joules. Now we are done with the introduction. Now we will go to circuit components. There are three circuit components we are going to study: capacitance circuit, resistive circuit, inductive circuit. Let us capacitance circuit. Consider two identical plates, both without a net charge. Initially there is no net charge. Two identical plates are considered and a distance S. If a small positive charge delta Q from A is moved to B, then A acts as what? Has a negative charge, B has a positive charge. Why? Because A is giving a delta Q and the small amount of charge is giving to B. So it is becoming less. Here the charge is becoming less. So it is negative charge, and it is gaining the charge, what is the positive charge. Work is done in moving delta Q from A to B because there is a force on delta Q returning delta Q to E. What they are telling us, what it is told is that work is done. How a charge is moved from A to B, and the charge want to go back to A. So there is some force attracting to A that it should return to A. So to overcome that force and bring the charge to B, there is some work required. No, so work is nothing but what? Force into displacement. With a force moving to one point to other with some force, right? Accordingly, if plate B has a positive potential with respect to A, P is positive and A is negative. When a second small positive charge of same magnitude, delta Q, is taken from A to B, the force is larger and the work done is greater. If some more charge is taken from A to B, then what happens? Then the force is also larger and the work done is also greater. The process is linear if delta Q is sufficiently small. Hence, we can say that charge is proportional to potential difference V. Q is directly proportional to V. Q is charge, V is potential difference, Q is equals to CV. Here C is capacitance, C is equals to Q by V. A new unit of capacitance is farad, F. The energy expended at any point in the process of transferring charge from one plate to other is shown in this region. To know the total energy required to transfer Q coulombs of charge resulting in the final potential V, what we can do is, you need to take the area of this triangle. Area of the triangle is what? Half into base into height. So W is equals to half into, this is base, that is Q, and height V into Q, half into V into Q is nothing but CV, half into C, V square joules. This is the total energy. The potential difference V between the terminals of a capacitor is proportional to charge on it. V is proportional to Q, or V is equals to Q by C, as we have seen before. C is the constant of proportionality and is called the capacitance. I is equals to dQ by dt. We know that Q we can take it as here Q is equals to CV. So if you substitute Q equals to CV, then what we get? C into dV by dt. dV by dt. C into dV by dt. So V is equals to 1 by C integral I dt. What happens is, when this derivative is moved this side, then it becomes integration. So V will become equals to 1 by C comes down, 1 by C integral I dt. Then let us consider a voltage V is equals to Vm sin omega t. If V is Vm sin omega t, we applied across a capacitor of C farads. Then this equation comes, I is equals to C into dV by dt, C into d by dt, Vm sin omega t. Then this equation appears, Im sin omega t plus pi root 2. Now, by comparing these two, what we can say is Vm is equals to Im by omega c. So Vm is equals to Im xc. 1 by omega c is equals to xc, reactance of the capacitance, capacitive reactance. Capacitive reactant xc is equals to 1 by omega c. Here xc, capacitive reactance xc is equals to 1 by omega c. This is important. Whichever I have marked with red, these are the important things you need to remember. Then capacitive circuit is done now. Now we'll go to resistive circuit. What is resistive circuit? As we have already discussed, resistivity, resistance, what it is doing, it is opposing the current. See, if you see, there is a resistance, current is going, and there is a potential difference across the resistance. The potential difference V across the terminals of a resistor R, as in figure 1.3, is directly proportional to the current flowing through it. V equals to IR. This is nothing but Ohm's law. V equals to IR. V is proportional to I. The potential difference is proportional to I. V is equals to IR. R is resistance, I is current, V is potential difference. This is also important. When a sinusoidal current I is equals to Im sin omega t is applied to the resistor, then the potential difference will be V equals to R into Im sin omega t. R into Im is what? We know. R into I is V. So Vm sin omega t. RMS value of voltage V is equals to Vm by root 2. RMS value will be when V is nothing but Vm by root 2. Vm is nothing but maximum voltage is equals to Vm is nothing but what? Im into R. Im into R by root 2. That is equals to Ri. V is equals to Ri. No? Ri. So where the RMS current of I is nothing but what? RR get cancels. I is equals to Im by root 2. V is equals to Vm by root 2. I is equals to I max by root 2. V max by root 2 and I max by root 2. These are the RMS values. Ohm's law can also be expressed in terms of conductance. As we have already seen, conductance or conductivity is inverse of the resistance, or resistance is inverse of the conductance. So, if you can see, V equals to IR. Inverse of resistance means I is equals to V by R. I equals to V by R. I equals to V by R means I is equals to V into 1 by R. 1 by resistance. 1 by resistivity is nothing but what? Conductance. So I is equals to GV. This is also important. The volt ampere plot of a linear resistor is a straight line, and that of many devices are non-linear, such as diode, for which Ohm's law holds good for after linearization. The power absorbed by a resistor is given by P is equals to VI. We have already seen voltage into current. V is nothing but what? By Ohm's law, IR, that is equals to I square R, that is equals to, we can write here, say P is equals to VI. No. Then V is nothing but what? IR. That is equals to IR into I. That is I square R. I square R. This is what we got. P can be written as VI, and in other terms I square also we can write, and in other terms also we can write. In V square by R terms also we can write. In terms of V, that is nothing but V is equals to V into I. We know that I means what? V by R. No. I is V by R. Then that is equals to V square by R. See, V square by R. This all is done using the Ohm's law. Here V is nothing but IR, and here I is taken as V by R. So V square by R. Then from the definition of average value, we have P average is equals to 1 by T integral 0 to time period T I square R dt is equals to R, will take it outside, integral 0 to T I square dt. This is nothing but I square RMS into R. P average is equals to V square RMS by R. These two are also important. Then now let's see the linearity test of the resistive circuit. To understand the concept of linearity, let V1 and V2 be the what? Voltage applied, and I1, I2 be the current, and voltage across the resistance R, and P1 and P2 be the power. V1 we know it as I1 into R. P1 is nothing but I1 square R. In the previous slide only we have discussed. V2 is what? I2 into R. P2 is what? I2 square into R. Now applying voltage, V is equals to V1 plus V2. If total voltage is equals to V1 plus V2, what we get? V1 is what? I1R. Then V2 is what? I2R. Then what we get? R common, I1 plus I2 into R. The above equation tells that whenever excitations such as V1 and V2 add up, the responses I1, I2 also add up. This is known as linearity test. So we are getting the nothing but the I is multiplied with R. The same we are getting. Separately and adding also we get the same. So it is nothing but it is linearity test. It is obvious that the linearity test does not hold for power relations. In fact, power relations are not linear. Power relations are not linear. Why? Because if total power P is equals to P1 plus P2 is taken. So P1 is what? I1 square R plus P2 is I2 square R. R if you take common, I1 square plus I2 square. What is happening here? Here the I is getting squared. Okay, so the linearity does not hold good, but for voltage the linearity holds good. Need to remember that power does not hold good the linearity and it is non-linear, but voltage is linear. It passes the linearity test. Resistance calculation. The reciprocal of rho is resistivity. This is resistivity and this is conductivity. This is conductivity and this is resistivity. The conductivity of the material, the resistance R of the conductor varies directly with the length I and is inversely proportional to the cross-sectional area A. That is, R is directly proportional to L. R is inversely proportional to 1 by A. R is equals to resistivity rho into L by A. This is an important formula. They may ask questions and sums also on this, where rho is the proportionality constant. It is called a resistivity or specific resistance and its unit is ohm meter. The specific resistance or resistivity rho represents an opposition to the flow of electricity. The reciprocal of rho, that is resistivity, is the conductivity, that is sigma, the conductivity of the material. Conductivity represents the ease of flow of electricity. Nothing but we have seen resistivity and conductivity in before. This is a formula for the resistivity and the resistance, and conductivity unit is what? Mho. This is ohm meter. This is mho, or SI unit is Siemens. Mho is represented in this way. Ohm meter is represented, this is ohm meter. Okay, and this is mho. Mho is it is written in the ulta of ohm, like this. So mho meter. Conductivity is mho or Siemens. And now let us see an example with this formula. Determine the resistance of a 1 km strip of copper of rectangular cross section 2.5 by 0.05 centimeter. The resistivity of the material is 1.724 into 10 power minus 8 ohm meter. It is 10 power minus 8 ohm meter. What we can see here is, say rho is given as 1.724, then L is given as 1 kilometer, A is given as cross section, that is 2.5 into 0.05, rectangular cross section. This is length, this is breadth, so we multiply both and into we are converting into meter square, so into 10 power minus 4, 1.25 into 10 power minus 5 meter square. Substituting the values, what we get, R is equals to rho place, will substitute this value, L is 1 kilometer and area is 1.25 into 10 power minus 5 meter square. So we'll get 1.38 ohm. Commercial resistor. Now let us see how resistance coding is done, and if you people have seen the resistors, then you can see that there will be color coding on that mentioned, like 4 strips like this, A, B, C, D. The A, B, C, D is not mentioned, but like this color strips are present, and this is how it looks. If you see on the resistor, the first A, this A component, B, C, D is there. No? This A, first one is A, first digit, and B will be the second digit. This C will be the multiplier and D will be the tolerance. See, these are the commercial resistors with different colors: black, brown, red, orange, yellow, green, blue, violet, grey, white, blue, gold, silver. And this is these are the digits. if you say this, we need to take the digit. For this we need to take the digit. If this, the third one, what we need to take, this multiplier thing we should take. Then if there is a tolerance, we should take the tolerance, that is plus or minus 1%, 2% tolerance we need to take. We'll understand first. We can remember this with the easy thing. What is that? BB, this is B, no, start with B. B R O Y G V V G. BB Roy of Great Bengaluru has very good wife. And gold and silver, you need to keep it, you need to remind like that only. See, BB Roy of Great Bengaluru has very good wife. You can remember in this way, so that after writing this, you can write 0, 1, 2, 3, 4 till 9, and into 1, 10 power 1, 10 power 2, 10 power 9, plus or minus 1%, 2%, 3%, 4%, and these percentages you need to remember. 0.5, 0.25, 0.1, 0.05. Okay, this is the easy way you can remember this. Here, if we'll see one example: red, brown, orange, silver. First one, red. Red one, what we should take? First color is red, means first digit we should take. Digit, what is the digit? Red, 2. So 2 we need to write. Second digit, what is second digit? Brown is given. So brown. Brown's digit is what? 1. So we need to take 1. Okay. Then multiplier. Third one we need to take as multiplier. So orange. Orange multiplier is into 10 power 3. So 3 zeros we have written. Then tolerance. The last thing is tolerance. Silver. Silver has a tolerance of plus or minus 10%. So we'll write. We'll take one more, like brown, black. See, here brown is first digit, no, 1. We'll take 1. Black is second digit, so 0. Then brown, black. Only this much we have, and in plus or minus 20% tolerance should be there. Why? Because see, this black, first brown, black 0, and black has a tolerance of 20%. Here it is not mentioned, so we need to take 20% ohms. Then brown, black 1, 0. Gold is what? Gold is having the multiplier of 10 power minus 1, 1 by 10, nothing but 0.1, and the silver tolerance is plus or minus 10%. So we multiply this, we get 1.0 plus or minus 10% ohms. Like this we calculate the resistors, the value of the resistors. Like we say, no, 1.1K, 1K, how it has come? By this only, by this color coding only we can guess which resistor. Why? Because on resistors we don't have the which ohm, how many ohm. By knowing the color coding only we can find the resistors value. Temperature effects of the resistor. The ambient temperature is the temperature of the gas, liquid or solid surrounding a resistor. When the ambient temperature is varied, a change in resistance is noted. A temperature increases causes molecular movement within the material. When the ambient temperature is varied, what happens is, then the resistance is noted. The temperature increases causes the temperature, as there is an increase in the temperature, molecular movement of the material also changes. As you see, when you boil the water, as the temperature is increasing, the liquid changes its movement. No, the molecular movement can be seen. The drift of free electrons through the material is impeded. This fact causes the electrical resistance of the material to rise and is called the positive temperature coefficient. On the other hand, temperature increase in certain materials, particularly semiconductors, creates many more free electrons than existed in the clueless state. Often this increase in the number of free electrons decreases the resistance of the material with an increase in the temperature. This is called negative temperature coefficient. These are the two temperature coefficients. The resistance values R1 and R2 at temperatures T1 and T2 respectively can be written as how? R1 is equals to R0 into 1 plus alpha T1 minus T0. R2 is equals to R naught 1 plus alpha into T2 minus T naught, where R naught is the resistance value at T naught is equal to 0 degree. At initial, what is the resistance we have noted? No, that is R naught, and alpha is what? Temperature coefficient. After simplification, what we get? R1 by R naught or not? No, we can equate these two. So R1 by 1 plus alpha T1, that is equals to R2 by 1 plus alpha T2. We will see an example for this. The resistance of a copper motor winding at a room temperature 20 degrees centigrade is 3.42. So R1 is 3.42. After extended operation at full load, the motor winding measure 4.22. So R2 will be 4.22. Determine the rise of temperature. The temperature coefficient alpha is 0.00426. The temperature increase they are asking. Temperature rise. T1 is then the T1 is the initial one for R1 is 20 degree. T2 they are asking. The resistance temperature equation is R1 by 1 plus alpha T1 is equal to R2 by 1 plus alpha T2. If you substitute R1 and T1 alpha values, then T2 you get it as 79.6 degrees centigrade. Therefore, the rise in temperature. Here you will get T2 value. But the rise, how much rise it has changed means what will get? Then T2 minus initial T1 you get the total rise in temperature 59.6 degrees centigrade. Now the last circuit, that is inductive circuit. If the current I flowing in an element of figure 1.5a, if there is a current I flowing changes with time, the magnetic flux phi produced by the current also changes. See, if the current flowing I in an element changes, if the current is changing, then the flux also produced also changes, which causes a voltage to be induced in the circuit. What happens because of this? Because of the change in current and the change in flux, there is a voltage induced equal to the rate of change of flux linkages. That is V is equals to d phi by dt. V is directly proportional to di by dt. So V is equals to, here phi is nothing but phi is equals to Li. Flux is nothing is equals to L into I. L into current. L is a proportionally constant self-inductance into I. Okay. Here this you need to remember, so that V is equals to d phi by dt. If what they are telling, there is a change in current, so there will be the magnetic flux produced. So there is a change in flux also. There is a change in current, there is a change in flux, then there will be a potential voltage potential or voltage to be voltage is induced. So V is equals to d phi by dt, and V is directly proportional to di by dt. So as phi is equals to Li, if you substitute in the place of phi Li, then L we can take it out, di by dt. V is equals to L into di by dt. This is important formula. Then L is what? A constant of proportionality and is called the self-inductance, whose unit is Henry. Hence L is equals to d phi by dt. Here L is equals to d phi by dt, change of flux linkages per ampere change of current. In the circuit, you can see N is equals to number of turns in the coil B. Number of turns, these are the turns in the coil B, and E is equals to induced EMF in coil B, then induced EMF. This is the turns of the coil B, and induced EMF. Phi is equals to magnetic flux in Webers. Phi is, we have already seen, that is magnetic flux in Webers. The changing magnetic flux in the core, phi changes whenever current I changes through the coil, passes through coil B, changes through the coil A, passes through coil B. Therefore, there is an induced EMF in the coil B. So, E is equals to N into d phi by dt. Induced EMF is equals to number of turns in the coil B into d phi by dt. Again, the induced EMF is proportional to di by dt. That is, E is equals to L into di by dt. Why? Because phi is equals to Li. So, L into di by dt. As di by dt is directly proportional to d phi by dt, dϕ by dt. Comparison of these two equations, what we get? N phi is equals to Li. Here you can see that here E is equals to d phi by dt. Here E is equals to n phi by dt. If you compare these two equations and they are directly proportional, n phi is equals to this n phi equals to Li. We can equate both. Why? Because E on the left hand side it is same E. So n phi is equals to Li. In the context, it may be noted that an inductor is a device while inductance is the quantity L. Now L is equals to, here L is equals to n phi by I. The magnetic flux phi is equals to MMF. MMF is nothing but magnetic motive force by magnetic reluctance. Magnetic motive force is equals to Ni. Magnetic reluctance is directly proportional to length of the coil 1 by cross sectional area, and it is inversely proportional to 1 by cross sectional area. Magnetic reluctance is equals to 1 L by mu A, where mu is the magnetic permeability and is a property of the material of the core. This is how the equations are taken, and the energy stored can be found integral T0 to T1 Vi dt. Integral T0 to T1 Vi is what? L into di by dt into I dt. V is nothing but L into di by dt, no? Then I into dt, L by 2 I square T1 minus I square T0. The net flow of energy over the interval T0, T1 can be either into or out of the inductive element depending on the relative values of I square of T and I square T0. Now for the linearity relationship, let us consider V1 and V2 as the voltages and I1 and I2 currents. If I is equals to I1 plus I2 applied to an inductor, we get what? V1 is equals to L into di by dt. V2 is equals to L into di2 by di2 by dt. Then V is equals to L into di by dt is equals to L into di by dt. I is what? I1 plus I2. Then L into di by dt plus L into di2 by dt. That is nothing but what? V1 plus V2. What they are telling is there's a voltage, here voltages add up as current add up. Initially we considered the currents are adding up, but later on after simplification we can see current voltages are all add up. Voltages add up if the currents add up. If the currents add, voltages also add up. Hence relation V is equals to L di by dt is linear. We can prove it as a linear. Okay. Similarly, the current relationship in capacitor. This is voltage relationship in inductor. In current relationship in capacitor, what we have studied before, I is equals to C into dV by dt is also linear. Circuit components is done. Don't worry, these are the basics. You need to know the different components, how they work, how resistance, how their linearity, and how the energy is found. These are the basics and important things, so that you should know them. Later on you have sums. Sums are very important in this subject. So later on we'll deal with many as subjects, and I'll give you practice questions also. Don't worry, the circuit components is like some derivations kind of things, so that you should know the how resistance behaves, how inductor behaves, how capacitor behaves. That's it. This is the basics. Don't worry about those all equations. There are, I have mentioned some in red, the formulas in red. Those formulas are important. You should need to remember those formulas related to resistance or capacitor or inductor. You need to remember those formulas. Other than that, don't worry. Then now we will go to definitions. Definitions. Circuit element. Any individual circuit component, inductor, resistor, capacitor, generator, etc. with two terminals by which it can be connected to other electric components is called circuit element. See, these are the circuit elements like resistor, inductor, capacitor with two terminals. Then branch. A group of circuit elements usually in series and with two terminals. Branch is nothing but, if you draw like this, a resistor, and another resistor. This another, here what is happening, it is dividing into two branches. It's nothing but branch. Okay. Then potential source. Potential source, a hypothetical generator which maintains its value of potential independent of the output current. An AC source will be indicated by a circle enclosing a waveline. See, this is the AC voltage, this is the DC voltage, how we represent. This is nothing but potential source or voltage source we say. Current source, a generator which maintains its output current independent of the voltage across its terminals. The current source will be indicated by a circle enclosing an arrow for reference current direction. See, this is the current. How it is shown, how they are, basically these definitions are what means, we need to know what is resistor, what is inductor, how capacitor is drawn, then how battery is in DC voltage, how it is drawn, in AC voltage, how it is drawn, how current is represented in the circuit. So these are the definitions. Network and circuit. Network and circuit, there are networks and circuit means it is a combination of resistor, inductor, capacitor, or resistance with battery and some resistors, many more resistors. These all are like T network, pi network. We'll study in brief in future topics. Lumped network. Lumped network is nothing but a network in which physically separate resistors, capacitor, inductance can be represented. These are the lumped networks. As you can see, like lumped distributed. Lumped networks means R and C. Different separate resistors or capacitors and inductors can be represented. Distributed network is what? One in which resistor, capacitor, and inductors cannot electrically separated and individually isolated as separate element. A transmission line is such a network. See, it is distributed. RC. It is distributed. We can't separately and individually we can't isolate like this. This is lumped. If you can isolate, then it's a lump. If it is cannot isolate, then it is a distributed. Passive network, a network containing circuit elements without any energy sources. Passive network is nothing but passive network is something like resistor is a passive network, capacitor is a passive network, and inductor is also a passive network. Why? Because the other components other than voltage and source, voltage and current source, all are passive network. Why? Because passive networks are nothing but they are taking the energy from some other element like voltage or current source. But active networks are not like that. Active networks are voltage source and current source, which they give energy to resistors, capacitors. Nothing but what I'm telling is that this battery is a active network. Why? Because it is providing energy to the resistor. Resistor is a passive network. It is not providing any energy to anyone. It is just taking energy from the battery. So it is a passive network. Linear element. Circuit element is linear if the relation between current and voltage involves a constant coefficient. As you have seen many formulas, here also mentioned it again. V equals to IR, Ohm's law. V equals to L into di by dt, and V in terms of capacitor is V is equals to 1 by C integral I of dt. Mesh and loop. A set of branches forming a closed path with the omission of any branch making the path open. Mesh must not have any other circuit inside it. Loop may have other loops or meshes inside it. See, mesh means what is? This is one mesh and this is one mesh. See, ABCD is a mesh 1, ABCF is a mesh. In this mesh, there should not be any other loops or mesh. So this whole thing is a mesh. There should not be any other circuit or anything inside the mesh. But loop. Now let's see loop. Loop means what? This is one loop. This is two loop. And this whole thing also can be taken as third loop. 1, 2 and 3. 3 loops. Loops can have inside any other loops and other circuits also inside. Node or junction. A terminal of any branch of a network common to two or more branches is known as node. Voltage between any pair of nodes is a node pair voltage. This is node. Here, this is node or a junction. It is two branches it is dividing. No, this point is called as node. Vector and phase. Vector is a generalized multidimensional quantity having both magnitude and direction. vector is nothing but it will have both magnitude and direction. Direction is which has both magnitude, the value, and the direction also. Phasor is two-dimensional vector used in electrical technology which relates to voltage and current. Which phasor is nothing but which relates to voltage and current. These are the important definitions that you should know. What is resistor, what is passive network, what is active network, and what are the different loops, mesh, node. That's it. To analyze the circuit, we use this. These are the basics. Now we are done with what all? Introduction, circuit components and definitions. Now we are going to sources of electrical energy. There are two types of sources of electrical energy. What are those sources? Nothing but active sources. What we have studied, that they give energy to other elements, that is ideal voltage source and ideal current source. An ideal voltage source is two-terminal element which maintains a terminal voltage V of t regardless of the value of the current through its terminals as shown in figure 1.18 A and B. 1.18 A and B. See, there is a ideal voltage source. This is a voltage source. This is a voltage. This is a we can represent in the both ways, like this plus minus also, like this also, DC voltage. Then a VI plot of the terminal voltage current relationship for an ideal voltage source is how the VI characteristics are seen. See, this is the how the VI characteristics. It is independent of the current, regardless of the value of the current, how it is shown. At any instant, the value of the terminal voltage is constant. At any instant of time, the voltage is constant. This line represents it is constant with respect to the current value I. Whenever V is 0, the voltage source is same as that of the short circuit. Symbolic representation of dependent or controlled voltage source is this. This is a dependent voltage source. How dependent voltage source is represented? Dependent voltage source is represented. These are the independent voltage sources. These are the dependent. Dependent is represented by this diamond shape. If diamond shape plus minus or diamond shape arrow mark is shown, then these are dependent sources. These are independent sources. They don't depend on anything. These are dependent. They are dependent. In a practical voltage source, the voltage across the terminals of the source keep falling as the current through it increases. This is the ideal voltage source. But in practically what happens? As the current through it increases, the voltage comes on. The behavior can be explained by putting a resistance in series with the ideal voltage source. This is ideal voltage source, a resistance. In any form we can represent this plus minus in a circle or in this way also. So they have shown both representations. Don't get confused. It can be represented in both ways. The source keeps falling. The sources keep falling as the current through it increases. As the current is increasing, the source is falling. This is what it will not be constant. It is ideal source, but if it is a practical voltage source, it goes on falling. An ideal current source is a two-terminal element which maintains a current I of t flowing through its terminals regardless of the value of the terminal voltage. In voltage source, regardless of the current. In current source, it is regardless of the voltage. The symbolic representation of dependent or controlled current source. This is the independent current source. Dependent, I told you, it should be in the, if it is in the diamond shape, then it is a dependent source. As you can see, the current is constant with respect to the voltage. There is no change. But in the same way, when it is a practical current source, when ideal current source is connected with a resistor which is parallel, then what happens is that as the voltage is changing, as the current will be like this. Behavior can be explained by putting a resistance across the terminals of the source. And in practical current source, the current through the source, the current will be decreasing as the voltage across this is increasing. As voltage is increasing, what is happening? The current is decreasing. Okay, but here what we can see in this B, the VI characteristic of an ideal current source is that which at any instant is simply a vertical line when I is 0. The ideal current source has the same VI characteristics as open circuit. Okay. Anywhere in the circuit, if you want to short circuit, then you can only short circuit the voltage source. Then the current source will be open circuit. The ideal current source is the same like an open circuit. And one more important thing is like voltage will be every time connected to series of resistance, but the current ideal current has the current with parallel to current source. See, parallel to current source, in voltage it is in series. These are the two important things we need to know. And this is the equation we have written by this circuit. I1 is equals to this total I minus V1 by R. To know these all things, how these equations are written and all, we need to know some laws and all. In further things we are going to study. Initially, you just remember what is ideal current source and ideal voltage source and how it is going to behave. That's it. And these are the dependent or control sources. I told in diamond shape if it is mentioned, so it is a dependent source. Even these dependent source also we will see in the circuits, so we need to remember them. What is that? Voltage controlled voltage source. See, here this is a voltage controlled voltage source, then current controlled voltage source, then voltage controlled current source, and current controlled current source. As you can see here, it is the value is written in the form of voltage, and it is a dependent voltage, so it is voltage. This is controlled by this value, so voltage controlled voltage source. Then here current is controlling, so current controlled voltage source. Here what? Voltage is controlling, so voltage control, this is current source, voltage controlled current source. And this is current is controlling, this is current source, so current controlled current source. These all are very important. The value here controlling is maybe current or voltage, but these two are the voltage sources, voltage dependent sources. These two are current dependent sources. You have done with introduction, the circuit components, definitions are done. And in circuit components, you have studied what is capacitance, what is resistance, and different things in resistance and inductors, circuits. These are the basics. We need to remember some formulas there. I've marked them with the red. Please go through it. Definitions, these are also basics. We need to know how to analyze the circuit. To analyze the circuit, we need to know the basics. No, for that definitions like mesh, what is loop, these all things are important. Just go with it. Then we have sources of electrical energy also we have seen, like voltage, ideal voltage source, ideal current source, and some dependent sources. These are important. Why? Because these all are seen in the circuits. If these are not known, we cannot solve the circuit. So we need to know the basics. So I stop this video till here. I hope you liked the video. I will be posting the next topics video in the next video, like source transformation, random network transformation, mesh and node analysis. So if we complete these 3 topics, we can complete the first chapter of the first module. So if you have any doubts, please do comment in the comment box. And if you want any other further information, so please do comment. I'm stopping this video till the sources of electrical energy. The further topics will be learned in the next video. Thank you. From Sri Sai Tech Edu. Read, lead, success. Don't stop reading.